Okay, thank you for the introduction. This is joint work with Eric Chen of CMU and my colleagues Shez Kadir and Riwan in Microsoft. So our work is about secure programming and verification of online services. Today, there are many scenarios where multiple parties need to be involved in a transaction. For example, third-party payment involves a merchant and a cashier. Sorry, can you see the mouse? And the single sign-on involves a relying party and an identity provider. And similarly, authorization is also a multi-party scenario. Unfortunately, plenty of logic bugs have been discovered. And according to the Cloud Security Alliance, these problems have become the #4 cloud computing top threat. And the consequences are serious. An attacker can purchase without making payment, log into other people's account without password, or obtain some unintended authorizations. So clearly, this situation asks for an effective program verification approach. And indeed, researchers have been talking about program verification for many, many years. But in reality, it is rarely put in practice by developers because of several practical hurdles that I'm going to explain in the next slide. So our work, CST, is to significantly lower these hurdles so that real developers can do verification. Now, first question, why is verification difficult in reality? Suppose we have a multi-party system based on protocol X. Now, some people may say that verification is not so hard because you just feed the source code into an automatic theorem prover or the model checker and your job is done. Well, that is, they miss a few very important things here. First, the source code has to be verified against a spec. So typically, protocol X is written in a document in English. So developers need to really understand the protocol text in order to come up with the specification for every party, which is not very easy. And second, the source code runs on top of the system platform, which need to be modeled. And furthermore, since we are talking about services, these source code expose public method that can be arbitrarily invoked by the attacker. So the modeling of the attacker and the platform can be very subjective and very challenging. Now, the third hurdle is that even after the modeling, the proof itself is still very challenging because the attacker is essentially a top-level loop that interacts with the system. So we are talking about an infinite state space here. And at the end, the developers need to convince the verifier that every possible transaction satisfies the safety property. And this kind of proof has to be inductive, which requires a very complicated loop invariant to be derived from the source code, which is very, very difficult, especially for real-world code. So now let's see what CST does. In CST, everything runs on top of the actual platform. And even the program verifier, which we call the certifier, even the certifier runs on top of the actual platform. And then I will explain later that CST is going to verify a system-wide multi-party property independent of any protocol. Now, CST doesn't need to model the attacker either because we just allow the user to interact with the system for real. In other words, every transaction just concretely happens in the system. And then at the end, the certifier checks if this transaction satisfies the system-wide property. So now let's see a toy example. We have 3 parties here. So you can see A.com has an integer A, B.com has an integer array B, and C.com has a Boolean C. Now this system wants to maintain a property C equals true if and only if there exists an item in B which equals A, okay? So we call this the ambient predicate, because it is defined over all the parties. It is about the global safety property. Now, this ambient predicate is great, except that it cannot be concretely checked, because the certifier on C.com does not have the concrete value of the secret int A and the array B. Right? Now, what can we do here? Our CST approach is essentially that during the execution of the transaction, we just collect the executed source code from every party, and then at the end, we symbolically check the ambient predicate using the collected source code. So I know that this is a very high-level description, but please bear with me. I'm going to use third-party payment as a concrete example. In this system, there are three parties: the client, cashier, and merchant. Now let's call the first message place order request, which invokes a method on the merchant called place order. Then this method generates a redirection to bring the client to the cashier, where a method pay is called. Now this method generates another redirection to bring the client to the merchant, where complete order is called. Now the merchant at this moment can decide to accept or reject the transaction. Okay. Now, what is the safety property here? We realize that the safety property is actually very, very intuitive. Essentially, what we want is that at the end of the transaction, the order to be checked out must have been paid on the cashier. Right? This is common sense. And more specifically, we want to check that there exists a payment on the cashier of which the status is paid, the total equals the gross amount of the order, and the payee is this merchant, and the payment is for this particular order. Right? So this is our ambient predicate. This is what we want to ensure by the whole system. Now let's see what a traditional implementation does. So here I'm showing you a real implementation called nopCommerce, which integrate Amazon payment. So you see these are the messages, and you can see that this pay request is signed by T-Store, which is the merchant running nopCommerce, and you can also see another message is signed by Amazon. So these digital signatures make sure that the client cannot tamper with the messages. Okay, so far it looks good. Unfortunately, this implementation is vulnerable. It allows an attacker, Mark, to pay to his own store, like Mark's store, but still check out an order from the victim tstore.com. So the details are in the paper, which are not very important for my presentation. What is important here is that in a traditional implementation, every party just do some local checks. But the most important ambient predicate is nowhere to be found in the whole implementation. So wouldn't it be great if we can enable developers to explicitly check the ambient predicate? That will make sure that we have an end-to-end safety. So here comes our CST implementation. The only addition that CST introduced is a message field called SymT. It's called SymT, or symbolic transaction. And initially, SymT is empty. But after the execution of the first method, now the SymT becomes tstore.com : hash place order. Now this hash place order is the SHA-1 hash value of the source code of place order. Right? So this transaction goes on, and eventually, after complete order is executed, the final SymT is this long string, which consists of the three steps. Now we just pass this final SymT to the certifier. The certifier's job is to assume that T-Store and Amazon are the only trusted parties. And then it's tried to verify that this sequence of computations logically implies the ambient predicate. So this is a symbolic check. Now let's see the internal of the certifier. The certifier consists of a cache, a program synthesizer, and an off-the-shelf C# program verifier. So here you also see the 3 pieces of input that I showed in the last slide. Initially, the cache is empty, so the input arrives at the program synthesizer, which does 3 things. It discards untrusted steps, and stitch together trusted steps, and assert the ambient predicate. So in this case, we can see that this is the synthesized program, which basically the synthesizer just stitch together these 3 method calls and then put an assert at the end of the program. So in this case, these 3 method calls are sufficient to ensure the ambient predicate. That's why this verification is successful. Then it's write the verification result into the cache, and in the meanwhile, this transaction is accepted. Now, on the other hand, if the previous attack is launched, then this is the final SIMT, and you can see that the first step happens on a party called markstore.com, which is not trusted. Then as a result, when we synthesize the program, it only consists of the 2 method calls. And the first method is skipped. So as a result, these 2 method calls are insufficient to imply the ambient predicate. So in this case, it is not, it's not verified, then this transaction is rejected. Okay? So I just explained to you how CST works, but very briefly. We have applied CST on many open source ASP.NET solutions, including 2 third-party payment solutions and 3 single sign-on solutions. We also built a gambling scenario, which include a gambling site, a cashier, a token manager, and a coin tosser. So we put these 4 all together. So all our systems are accessible through the page, through our project page. So we measure the lines of code that we added or changed in this project, and the numbers are always below 200 lines of code for every party. For performance, because of caching, we are able to achieve a near 0 amortized runtime overhead. And for security, we selected 14 known vulnerabilities, and we conclude that 12 of them are logic flaws that CST is able to prevent, and 2 of them are not, including a signature validation flaw and client-side same origin access violation. Now, I want to say that a very big advantage of CST is protocol independence. Now, to show this, we come up with several implementations, obviously violating OAuth 2.0, but CST is able to make sure that they are all doing authentication correctly, although they violated the protocol. Now, let me briefly talk to you what we did. So here you see the original protocol flow, which is doing single sign-on authentication. And our first question is, why do we need this app secret for authentication? So we just remove it. And it's turned out that we can still do authentication correctly without this field. And then we started to violate the protocol more blatantly. We use access token to replace the authorization code in this method call. And this is explicitly forbidden by the protocol, by OAuth 2.0. But we realize that as long as we move this check to the second call, this flow is still doing correct authentication. Now, if you insist that this is not OAuth design, the identity provider should absolutely check nothing, then the flow can still be secure if the relying party checks everything. Right? So I guess my point here is that for a complex protocol, it is very difficult to understand exactly which party should do what and why. So it is much better to just verify that all parties collaboratively satisfy a system-wide property. That is more intuitive. So to conclude, CST is unique because it sits on the middle ground between static verification and runtime checking. In fact, it is doing symbolic checking at runtime. And CST reduces burdens for developers because it is able to verify a system-wide multi-party property. It reduces the burden of modeling, and the CST's proof obligation is not about all possible transactions. It is only about the transaction at the moment. So please visit our webpage, and I'm happy to take questions. Yeah.